We're going to work on partial fraction decompositions. What this really comes down to is taking a sum of fractions, taking the answer that we would get from that, and then working back to the original problem. So we've seen how to add regular fractions together, like 1/2 plus 2/3. We've also seen how to add rational expressions, so polynomials over polynomials, by finding common denominators. This process works our way backwards. We're essentially starting with the answer or the rational expression, then working our way back to much simpler fractions. We use this a lot in calculus. In calculus, it's much easier to apply the calculus techniques on smaller, simpler functions, and this decomposition process accomplishes that for us. We are going to see some vocabulary as we move through. I really just want to dive in here and go ahead and start with an example. So in this example, I'm going to go ahead and add these two fractions together. What we're going to be learning here is actually the process working our way backwards. But it's great to see what this looks like going forwards so that we have a reference point. When I want to add two fractions together, I need to find a common denominator. For this one, my denominators are both very different. So I can go ahead and just multiply those two together to come up with my LCD. So x plus 2, x minus 1. And by very different, I mean they don't share any factors. So I go ahead and take each of these fractions, and I'm going to multiply by the missing factor. I'm building my common denominator. This one is missing the x minus 1 in the denominator. The second one already has the x minus 1, so I'm going to multiply in the x plus 2. As I just continue to simplify here, I get that denominator that I was looking for, x plus 2, x minus 1. In my numerator, I've got some things. Let me go ahead and just circle them in yellow here. I've got some distributions to do. So let's go ahead and distribute the 3, then distribute the 4, and then we can simplify what we've got. So I get a 3x minus 3, so 3x minus 3, and then distributing that 4, I get a plus 4x plus 8. I can multiply out that denominator as well, just doing FOIL. I get x squared, that would be plus 2x minus x, so plus x. 2 times negative 1 is negative 2. In my numerator, let's go ahead and collect like terms. 3x plus 4x, we get 7x. And then negative 3 plus 8 is plus 5. This is what we're going to be starting with. The decomposition over here, this is going to be our goal. And we are going to be working this process backwards. We're going to be factoring to get that denominator. So if we just kind of move backwards here, we're going to be factoring to get the correct form of the denominator. We're going to be multiplying in these missing factors to work our way back. A couple things we need to work on vocabulary-wise and definition-wise before we can go ahead and start moving into our process. So we want to talk about proper fractions. If I'm talking about just normal numbers, 2/3 would be a proper fraction, but something like 7/3 would not be a proper fraction. And that's because the numerator is bigger. So this one is not a proper fraction. We're still going to use that same concept that the numerator needs to be smaller than the denominator, but these are polynomials. So instead of just saying smaller, I need to say the degree. So the degree of that numerator, here it's f of x, is smaller than the degree of the denominator, which is g of x. Let's take a look at these templates. As we build rational function decompositions, these partial fraction decompositions, we're going to be using only proper fractions. That's part of the breakdown process. And we're going to do this with degrees. So I see that the degree of my denominator here is 1. So this numerator needs to have degree 0. I'm building a template here. So this is going to be our starting place, our building block. I'm not going to know what that degree 0, which is just a number, needs to be. So we're going to just use capital letters to represent those constants or those numbers. For the next one, this one is degree 2 in the denominator, which means I need this numerator to be degree 1. Let me circle that. I need this one to be degree 1. Well, degree 1 is like a line, right? So that would be an mx plus b. That would be a degree 1 or a linear function. That's what I need in that numerator, except I don't want to use an m and a lowercase b. I'm going to go ahead and use my capital letters. So I'm using my capital letters, it would be ax plus b. Or you could use cx plus d, whatever capital letters. So I've got degree 2 and then a degree 1 numerator. Next, we've got a degree 1 denominator. So we need a degree 0 numerator, and this is just going to be a capital letter for that number. Here I've got a degree 2 denominator, so I need a degree 1 numerator. It would be y equals mx plus b, but instead I'm going to use ax plus b. And then last but not least, this guy is degree 1. So that means that I need a constant in my numerator, and you can use any letter here, right? I mean, it could be W. We probably won't get up as many letters as W, but just to kind of drive home the point, it doesn't matter what, but we're just using capital letters to keep our variables straight from what we're using for the constants. Okay, a really nice pattern though, as we're working through these. Let's go ahead and take a look at these examples in terms of whether it's irreducible. A polynomial is irreducible. IR means not. Reducible for polynomials means factorable. So it's irreducible if it's not factorable. So I can't factor it any further. Okay, for this first one, x minus 3, I'm just looking at the denominator. Can't factor that any further. X squared plus 4, that's a sum of squares. I cannot factor a sum of squares. So are those irreducible? Yes. So I don't need to do that second part. So I'm ready to go ahead and build my template. My template's going to have factors of the denominator, x minus 3 plus x squared plus 4. Now I take a look at those degrees. So I've got a degree 1 here, a degree 2 here. So I'm going to go ahead and create numerators to make these proper fractions. So I need degree 0. So that's just going to be a constant, letter A. Degree 2 denominator, x squared plus 4. I need degree 1. So that's going to be bx plus c. Okay, next. Is my denominator irreducible? No, I can reduce this guy further. So no, I am not done with that one. I can reduce this one further into x plus 1, x minus 1. That's an x with a 10 in my numerator. So as I break this one down into the template, x plus 1, x minus 1, these are both degree 1. So I just want constants in the numerator, a and b. Okay, next one. Can I factor 12x squared plus x minus 35? I think I can. So I'm going to guess, and we'll do it off to the side here, that this one probably is reducible. Let's go ahead and try and factor this. And I'm going to factor it right here. We can erase it if we need to, if you're not writing in pen. I'm going to try, you could do 2 times 6. I'm going to try 3 times 4 first. So 3x and 4x. For the 35, that would be 5 times 7. And I need x in the middle. So 5, if I put 5 with that 4, that's 20. If I put the 3x with the 7, make this a little bit bigger, that's going to be 21. And I want that 21 to be positive, so plus and minus. So were these irreducible? No. I could work on this further. My numerator, 13x plus 33. Okay, here comes my template. 3x minus 5 plus 4x plus 7. These are both degree 1. So I'm going to get degree 0 or nice constants in the numerator. The next one, is this guy irreducible? X squared plus 10 is, but x squared, I actually could write that as x times x. We think of this as a linear factor. So it's degree 1 with multiplicity 2. I think this is one of the most confusing parts of the partial fraction template. So I do think of that as a degree 1. So is this irreducible? I'm going to say no. Excuse me. I'm going to say no, because I can rewrite this as x times x squared plus 10, and then my numerator. The template, though, is really interesting because it wouldn't make sense to have two x's, right? So instead I'm going to have one x as a denominator. I could also have an x squared as a denominator. So I'm going to go ahead and put in both of those possibilities, but that's just a multiplicity. So these are still linear factors. So this is still an a and this is still a b. This 2 that I've included here is multiplicity. Let me undo that so you can still see what I've got. So plus. So when you have an x by itself, the power is just multiplicity. So an x by itself, whether it's x squared or x cubed, is still going to get just a letter or a constant for the numerator. Okay, so what else? We've got the x squared plus 10. I don't want to forget that. X squared plus 10. This one is not an x squared by itself. So this one is degree 2. I need a linear numerator. Lines are mx plus b, ab, I'm on c, cx plus d. Okay, this one, x plus 1 quantity squared. Is this irreducible? You could kind of say it either way. I'm actually going to say no. It's a lot like the x squared example. I can write this as x plus 1, 3x plus 1. I know I didn't change much, but there's just a little more work to do. So no, I mean, kind of, right? But what's really important here is my template. And my template, I have multiplicity. So that means as I build my template, I get x plus 1, and I get another x plus 1. But it doesn't make sense to have the same denominator twice. So I'm going to go ahead and add my multiplicity to the second one, 2. Multiplicity 2. It's still linear, so I get an a over the x plus 1, and I get a b over the x plus 1 quantity squared. Okay, let's go ahead and do some examples now. I want to find the partial fraction decomposition for 10 over x squared plus 1. I'm going to start by factoring it. So 10 over x plus 1, x minus 1. Setting up my template, I get an x plus 1, x minus 1. These are both degree 1, so they just need letters a and b in the numerator. Next, I'm going to multiply by missing factors. So I've got 10 over, I'm just leaving the left alone for now. A over x plus 1 is missing the factors of x minus 1, top and bottom to keep it balanced. Remember, this is so much like what we did in the very first example. So in that very first example, I was right here multiplying in missing factors. So you're going to see a lot of similarities from that first example. Okay, where was I? And then the b over x minus 1, it needs to be multiplied by x plus 1s. My goal was to get the common denominator, and that's exactly what I got. I'm just rewriting the left. On the right, I'm going to leave the numerator. I'm not going to multiply it out, and you're going to see why here in a second. X plus 1. My denominator is the same, so I can combine these. X plus 1, x minus 1. Even if you have this in the different order, it doesn't matter. And this being the denominator, your denominators match. So I don't need to set those equal as I move into step 2. I'm trying to solve for a and b, and I'm going to do this using zeros. I'm going to go ahead and just equate my numerators. 10 is equal to a x minus 1 plus b x plus 1. So using what we know about zeros, I can get a 0 out of this first term by letting x be 1. I can get a 0 out of the second term by letting x equal -1. Let's go ahead and tackle x equal 1 first. We just do one at a time. So x equals 1. I'm going to move that through this equation where I've got my numerators equal. This is going to help me find a and b. So if I let x be 1, doesn't change the left at all, no x there, equals a 1 minus 1 plus b 1 plus 1. That is 0. looks like a 6, but it's actually 0. So I get 10 is equal to b times 2, so 2b. And that means that b is equal to 5. So I'm going to replace that with a 5. I can do the very same thing with my other zeros. I've taken care of x equal 1. Let's do x equals negative 1. I'm going to run that through the equation I've got up there in red. 10 does not change. A, replace x with negative 1. So negative 1 minus 1 plus b, negative 1 plus 1. Now that guy goes to 0. And I get 10 equals negative 2a. Divide both sides by negative 2. Negative 5 equals a. Negative 5. Put my answer in green here on the answer line. I've got my answer now. My goal was to find this numerator, so I've got negative 5 over x plus 1 plus 5 over x minus 1. So I was able to take that original fraction and break it down into a sum. Let's go ahead and do the next one. It's going to be really similar. So I need to go ahead and start by factoring. Sometimes they'll give it to you in factored form and you don't need to do this initial step. These are not those. So I'm going to go ahead and start with that initial step. So 7x plus 1. I'm going to factor that denominator, so definitely need x times x. And 6, we're going to do 2 times a 3. I want positive in the middle, so I'm going to make the 3 negative. Make the 3 positive and the 2 negative. Checking in the middle, negative 2x plus 3 gives me my x in the middle. Perfect. Also gives me my template, x minus 2 plus x plus 3. These are both linear, so they're going to get constant numerators. Here's where you can skip a step. So up above, we had this step right here. I don't need to worry about my denominator as soon as I have multiplied in my missing factors. So I'm actually going to do my missing factors just kind of right in line here. What I've got right here is my common denominator. So that means that A needs to be multiplied by x plus 3's and B needs to be multiplied by x minus 2's. But I'm going to go ahead and just ignore my denominators and let's just go ahead and set my numerators equal, just saving myself a step. 7x plus 1 is equal to a times x plus 3 plus b times x minus 2. Now I'm ready to go ahead and use zeros. And my zeros for this one are a negative 3 and a 2. Do that over here. I'll do that in blue. So as I'm using my zeros, I'm going to actually bring my equation over here, equals a x plus 3. You don't need to rewrite it if you don't want. X minus 2. I'm going to go ahead and start with a 0 of negative 3. So x equals negative 3. I need to run it through every single x that I see. So this is going to be 7 times negative 3 plus 1 is equal to a, negative 3 plus 3 plus b, negative 3 minus 2. I'll put a little box here so we can just follow our work better. So I get negative, this guy's negative 21 plus 1 is going to be negative 20 equals, that goes to 0. B, negative 3, negative 2, that's going to be negative 5b. Divide both sides by negative 5, and b is 4. Okay, that's nice. So b is equal to 4. So I've got that first numerator, so 4 over x plus 3. I've got one more to zero out, and that's using my second one of 2, so x equals 2. That's going to give me 7, so back to my, let me put a box around this guy, back to my numerator equation. Always going back here. I'm going to go ahead and plug in 2. So I get 7 times 2 plus 1 is equal to a, 2 plus 3 plus b, well, 2 minus 2 is 0. That guy goes away. 7 times 2 is 14 plus 1 is 15 equals, this is going to be 5a. Divide both sides by 5, so a is 3. So there's my other fraction. So I get 3 over x minus 2 plus 4 over x plus 3. Okay, I got it. One more? Yep, one more left to go. Ugly numerators, but we really don't care about the numerator so much. We care much, much more about the denominator. So to start anyway, so minus 106, factor, x times x. Okay, 24 is, it's 4 times 6. That's not going to get me to 5 in the middle. It is 3 times 8. Oh, that's going to do it. So I want 3 times 8. So 3 times 8. I want positive 5 in the middle. So I want the 8, since it's bigger, to be plus, and then minus here. Okay, let me get rid of these. I've got room for my template. Equals. So x minus 3 is a denominator. So is x plus 8, a and b. I'm going to go ahead and multiply in my missing factors for the common denominator. My first fraction is missing x plus 8. My second fraction is missing x minus 3. Comparing just the numerators, I get 6x minus 106 is equal to a, x plus 8, plus b, x minus 3. This gives me 2 zeros to work through. So I get a negative 8 and I get a 3. So let's go ahead and start using our zeros. And I know that I want to put everything into, let me just put a box around our equation so we can kind of keep our eye on what we're using. So as I work through my zeros here, I want to start with x equals negative 8. Moving that through my equation, I get 6 times negative 8 minus 106 is equal to a, negative 8 plus 8 is 0. That goes away. Plus b, negative 8 minus 3. Okay, so I need 6 times negative 8. Grab my calculator. 6 times negative 8 equals, and then I want minus 106. Negative 154. So I get negative 154 is equal to negative 11b. I want to just, no, not that one. I want to divide both sides, not by b, by negative 11. So I can solve for b. So then I can just go ahead and grab my calculator again, and then just divide this guy by negative 11. And we get 14. Excellent. Okay, so b is equal to 14. So as I'm putting my answer together, I can go ahead and do my second fraction. So 14 over x plus 8. Okay, let's do the other one. So the other one's going to be that 3. So x equals 3. I get 6 times 3 minus 106 equals a. 3 plus 8 plus b, that one's going to be times 0, so that goes away. So now I want 6 times 3 minus 106. So I'm going to use my calculator again. 6 times 3, I know that's 18. So 18 minus 106 equals, so we get negative 88. Negative 88 is equal to 11a. Divide both sides by 11, and negative 8 equals a. There's my first fraction. So negative 8 is my numerator. Negative 8 over this one here, x minus 3, and I put a plus sign in the middle, and I've got my partial fraction decomposition.